No? Why not? There's some error. Error in it ran for me, so obviously, what was the error? So we'll look at it and troubleshoot it. Try some more. If you don't get an error when you program, then there is something wrong. Either it's very correct or it's very, very wrong that you don't know what's happening. So making errors while writing coding is normal part of the process. So you just have to learn to plow through it and debug. And one of the good things about it is when you're writing models and you're trying to debug code, you end up learning a lot about what it is. So it's a very good learning experience. So instead of getting frustrating, you should see it as, hey, this is an opportunity for me to learn, so I'm going to try to learn. But we can take a look at some of the codes that you've written and see where we went wrong. What I'm going to do today is kind of switch gears and talk a little bit about why do we study groundwater contamination, or what were the drivers behind groundwater contamination, or what are the policies, and how did these policies come about. And so most of the discussion is obviously in the US context, so it will kind of give you an example of how United States went about doing these things. But I would certainly be very interested in keeping this as a discussion and trying to learn about what's happening in India, or what were the drivers in India, and how did things go about in India. Okay? So why did we start studying groundwater contamination? Okay? So for that you need to know a little bit of regulatory history in the US. And the first act, so till about 1960s, okay, there was not much environmental regulation in the US. Okay? A lot of it was simply people could essentially discharge their waste into the rivers. They could discharge their waste in unlined ponds, which basically meant that they were discharging it into groundwater eventually. So there was a lot of contamination, and there was this one river called the Cuyahoga River, and Cuyahoga River caught fire. Okay, so U.S. government is the only government in the world that has actually declared a river to be a fire hazard. Okay, so because why did the river catch fire? Can anybody think what would have happened in that river? So there was a lot of domestic pollutants, there was some industrial pollutants, but they added so much waste to the river that essentially the river turned anaerobic, okay, and started producing methane. Okay, and methane catches fire. It's a highly flammable substance, and there was a lot of industrial pollutants that were putting oil and grease and organic matter, which could catch fire. So you had something that there was a fuel. Methane is a fuel, right? And there was a substance to burn, which was all the organic matter. So it was only a matter of time before that river caught fire, and it did catch fire, and that really prompted. It was a very visual depiction for people to say, we need to do something about it. Okay. There was also a movement, an environmental movement, where people started looking and saying, okay, we are putting all these chemicals, we are putting all these pesticides, right? DDT is a very common example. There was a lot of DDT being used because it was one of the most potent pesticides that you can find in the world. And there was a lady named Rachel Carson, and she did some work that showed that the DDT that was being put was actually being transported all the way into Arctic, all the way into Canada, although a lot of that was being used in the southern part near the Mexico or the southern part of the United States. This DDT would undergo what's called as a long range transport, get transported several thousands of miles, and start thinning the eggs of birds. So the birds were being, what she found was, she was a biologist, so obviously she was looking at birds, and what she found was that the birds were being born with a lot of birth defects, or there was the mortality rate was very high. So there were a lot of eggs that were not hatching into hatchlings or like into birds. And she made the connection that this had something to do with DDT, of course. Of course, the industry that was making DDT basically said this is all baloney, this is bogus, there's nothing, there's no connection, whatnot. But several careful studies that were done led us to corroborate that hypothesis and actually prove that Rachel Carson was right. So there's a book named Silent Springs that Rachel Carson wrote. So if you all have a chance to read Silent Springs, it's a great read. It kind of talks about how environmental movements started in the world or started in the US. So right around that time when the Cuyahoga River caught fire, and then there was an growing environmental movement, people started saying, we need to do something to clean these rivers. Okay? So in 1970s or in 1969, government formed what is called the U.S. Environmental Protection Agency, and then he said, now this is the agency, you are responsible for making sure that people have good drinking water, but not only that, that our rivers are not polluted. So a lot of this was driven by rivers. Why? Why were rivers given particular attention and not groundwater? Because rivers were more polluted than groundwater? No? Well, more rivers are located. The one very simple reason why that happened is people could see the river. Okay, there was groundwater contamination, nobody saw groundwater. Okay, so but they could see the river was polluted. When they went swimming, they saw that there was stuff in there that they didn't like. The river was catching fire, so they said there's obviously something wrong. So the first act that came out is what's called as the Federal Water Pollution Control Act, and commonly this is referred to as what's called as the Clean Water Act, okay, or CWA. And CWA was passed in 1972. As I said, EPA was formed in late 1960s, 69, 68, and basically they were charged and said you need to come up with some federal regulation that tells that our rivers are clean, or our waters are clean. So that's what Clean Water Act did. And this Clean Water Act was actually modified a couple of times, once in 77, once in 87. There's been another amendment that people are working on. And the primary goal of this act was to make sure that surface water bodies, or the receiving surface water bodies that receive waste loads, okay, are clean. Okay. So somebody in the morning was talking about source control, right? Saying how do we control sources? This is how this is the federal regulation that controls sources. Okay, and the outcome of this act, the practical outcome of this act, is we created what is known as an NPDES scheme, or the National Pollutant Discharge Elimination Scheme. What that meant was, if you had to discharge loads into a river, so if you were a municipality, or if you were an industrial, if you were an industry and you wanted to discharge a load into that river, that discharge had to be permitted by the government. So you had to go get a permit, and the government would tell you how much flow you could put in and what is the concentration that you can put in. Okay. And that is based on a calculation known as the carrying capacity of the river. You look at the river and you say, okay, this river can clean up a certain amount, or certain things can happen. So based on that calculation, they came back and said you can put so much. Okay. Is it a good regulation or a bad regulation? Good regulation. Why is it a good regulation? So river has some self-assimilating capacity. So this is my river, right? And I have a city, okay, and the city creates some wastewater. So there is a wastewater treatment plant, or whatever you want to call it, and it discharges, right? And basically what this act does is it regulates the Q&C associated with that river. It says this is how much you can put in. Okay? Now there is another river, there is another city. It also has a wastewater treatment plant, and by the way, we don't, in the US, people don't use the word wastewater treatment plants anymore because somehow wastewater has a very bad connotation. No water is really wastewater. Water is good water. So we use what is called SPCS, or a permit compliance system. Okay, so because that system or that wastewater treatment plant complies with the permit of the National Pollutant Discharge Elimination Scheme or the regulations of the Federal Water Pollution Control Act. Okay, so now this guy is given some loading, right? How will that affect this guy? How will this person be affected? Will it reduce his loading, increase his loading? How many of you say reduces? See, I always have two answers. Okay, one of them is correct. So, how many of you are saying if this person is given a discharge of QC, a certain loading, okay, they are permitted. This is a permit. It's a legal document that says you can put so much pollutant into the river. What will it do to this person? Will that person's loading be reduced or increased, or stay the same? Reduce? Why? Downstream? So this guy's in the downstream, so obviously this guy polluted, so the ability of this city to pollute is gone down, right? Or so you say. Okay. So there are two things that you need to look at. One is Q, one is C. Okay. If I put C equals 0, okay, then will it help or hurt this guy? Correct. So if I put a very low concentration here, as a matter of fact, this guy's loading will help this person, this city. Okay. So what we try to do when we make pollutant discharge calculation is we're going to say this river eventually will go into some other big river, or this river has some things that has to have, there is some use for this river. Okay, people can either use this for drinking water, people can use this for fishing, people can use this for swimming, people can use this for contact recreation. They can be doing boating, they can do some non-contact recreation, like they can be on a boat. So we look at all these factors and say how much can we put, okay, but it has to take into account how much others have to put as well. Okay. So it's not a question of just looking at one individual entity, but looking at all the entities that are discharging. But in addition to all these, what are called point sources, there is a watershed and there is some land use, and when it rains, you get what are called as NPS, or the non-point source pollution. So these are not pollution that happens on a day in, day out basis, but it can happen when it rains sufficient enough that when it creates a runoff, it brings all the pollutants associated with it, dumps it into that river, and how do we manage non-point source solutions? Historically, we have managed point source solutions by putting treatment plants, and we have historically managed non-point source pollutions by regulating land use. Okay. We have said, okay, you can't, if you are going to do so much agriculture in this watershed, any more agriculture will cause problems. Okay. But there is really no regulation that says thou shalt not do agriculture, so dealing with non-point point sources pollutions has been a much bigger challenge in the US than it has been in dealing with point sources. We can very easily deal with point sources but not as much with non-point sources. So we continue to struggle with how to do non-point sources. So what does this all has to do with groundwater? So this is what the Federal Water Pollution Control Act told us, or the Clean Water Act, CWA as we call it. So that's what it said. Okay, it said that your receiving water body, that stream or a lake, we are going to restrict how much load we want to put in. If you look at it another way, what that permit is saying is, I'm giving you the right to pollute that stream, but only to this degree. Okay, so that's another legal way of looking at it, is to say that permit is giving you a right to discharge a contaminant that's otherwise not present in that system, with the understanding that that system will take care of it or somehow assimilate it. Okay, no mention of the word groundwater. Okay? So this act was a phenomenal act. Like, this is the first act in the history of the world where they came out and said, let's look at source water, let's look at source water control, let's try to clean up our rivers. Okay, and what this act did is, a lot of wastewater treatment plants were put in the 60s, 70s. Okay, in anticipation of this act, as well as a requirement that came out of this act. Okay, so the field of environmental engineering, pretty much starts with this act. Like, before that, it was mostly focused on household sanitation, or garbage or solid waste, but this act really put water in the forefront, and it said we need to somehow clean those rivers. They don't look good, and we obviously can't stop people from discharging water into that rivers, so we are going to regulate it. So that was in 1970s. Okay, what about 2017? What does this act do these days? What this act does these days is, a majority of stream segments in the US, a good chunk, okay, about 50–60%, are what we call our wastewater dependent streams. In other words, if there is no discharge coming from that treatment plant or PCS, there won't be water in that stream. Okay, so if you go and talk to the cities and you tell them, hey, I'll give you an option of you not discharging that wastewater, they'll be very happy. They'll say, yeah, great, I can use that water. One big reuse that happens in the US is, we take our wastewater and put it on our golf courses. Okay, because it's non-potable. Okay, it's easy. We want to grow grass, and nobody wants wastewater, so we'll put wastewater and grow grass and charge people a lot of money to come play golf, and works great. So the city can reuse wastewater very easily, but regulations now basically tell them, no, you can't, because if you don't discharge that wastewater, this town here, which depends on this stream, will not have the wastewater, will not have their drinking water. Okay, or there could be a fish that will require some amount of water be in that stream, because if that stream goes dry, then you're going to kill all that fish. Okay, so there are what are called as environmental flows, or downstream requirements. The downstream requirements are, there is another city downstream that wants that water as their drinking water, or there are environmental requirements, which means that the stream segment should have some flow to make sure that the species or the fish that is living in that segment continue to stay. Okay, so what does this mean to us? What it means is that we are always drinking somebody else's wastewater. Okay, so the choices that you have are, either you drink your own wastewater or somebody else's wastewater. Okay, there is no such thing as we drinking fresh water. Okay, but in the US, if you go and ask people, we'll take our water from this treatment plant, okay, put it in some reservoir, we'll put some water from this reservoir, and then we'll give you back the drinking water. Okay, this is what is called as a DPR, or direct potable reuse. Okay? So we want to directly use that wastewater for potable purposes or for drinking water purposes. What do you think people are going to say? What would you say? Okay, you are a city. I'm going to make this city your city. Okay, so your option is right now you're pulling water from this treatment plant from here, doing some drinking water treatment, and supplying it to the city. Okay, that's what is happening right now. So this city A discharges some waste. You pull it out, you treat it, you do this. Okay. So right now, people in the city are drinking that city's wastewater, basically. Okay. Now, we take this treatment plant, and instead of putting all the flow go down, we are going to go some there, and then put it back. Okay. So now the option is you're not, you're drinking a little bit of that city's wastewater, but you also get to drink your own wastewater. Okay. What do you think people will say? What do you think is the public reception to that? Come on, okay. If you were in this city, what would your position be? Okay. So a lot of things like this in the U.S. goes up for a vote. This is what we call a referendum. Okay. So on local elections, it will be on the ballot. It says, do you want to construct? Do you want the city to take a loan of several $1 million to construct a facility that will allow you to treat your wastewater and improve your water supplies? Okay, and there will be people who will be proponents of it. There will be people who are opponents of it. They will put a lot of ads in the TV and spend millions of dollars. Eventually, it goes to vote. Of course, the voting rate in the U.S. is very abysmally low. It's probably like about 10 or 20% of the people who can vote, and then it gets decided whether we build it or not. Okay, so how many of you are okay with this idea? Anybody? Nobody? So there's a saying in Telugu, like it says that your neighbor's sour dish is much better than the dish that you cooked in your home, because it's your dish, right? And it's not as tasty as the one cooked on the other side. So our neighbor's wastewater obviously is much more tastier for us than our own wastewater. Like so we choose not to. What's that? Well, we don't. So the problem is, if I say, okay, you don't want to drink wastewater, great. How about reclaimed water? Will you drink some reclaimed water? Yes, no, maybe. Okay. So these days nobody says wastewater in the U.S. Like if you say wastewater, they'll say, where did you come from? Which planet did you come from? Like so we use the word reclaimed water just to make it look good. And then we won't say it's a wastewater treatment plant. We call it permit compliance system. So there's a whole bunch of English language that has changed to make things palatable to people. Okay, but still people don't want to drink their own wastewater. I don't know why. Okay, you can clean it. You can put a treatment plant and clean this and make it cleaner than drinking water that you actually get from here. Okay, yet you will not drink it. Okay. So, but coming back to groundwater, this NPDES addresses surface water, but it does not directly address groundwater. Okay, it only addresses groundwater in the sense that if some of that groundwater actually goes and becomes surface water, what we call as base flow, then it's fine. Okay, but other than that, there is no mention of groundwater. So for a long time, what did people do? What do you think happened when this act came about? What this act did was it severely restricted people from putting waste into surface water systems. So what do you think people did? Okay. They needed to get rid of their waste somehow. So I said, okay, I can't put it in the river. I'll just dig up a pond and just dump my waste in there. So there was a lot of unlined, waste disposal pits created, and like cesspools or pits, whatever you want to call it, and people would dump waste into it. So this went about to about most of 1970s. This is what happened. Okay. Then there was a city in Massachusetts. Okay, and what people saw in that city of Massachusetts was they were alarmingly getting cancer. Okay, so the city had a very small town, like there were about 10, 20,000 people. I shouldn't be calling it a city. It's not a city by any standards, but all of these people worked in a company, okay, that made trichloroethylene, and they all were, the incidence of cancer was very, very high. Okay, people were, typically if you take a city of 10,000 and let's say there were 5 people who had cancer, right? I mean, or 10 people who had cancer, this place had like 200 or 300 people that had cancer. Okay, and interestingly, there was this one neighborhood in the city or one portion of the city where almost everybody had a cancer. Every house there was somebody who had a cancer. Okay, so this is what we now call as a cancer cluster. Like so this is where spatially there is a group of people that has unusually high cancer rates. So we were saying, why is this happening? Okay, and turns out the major people in that town, W.C. Gray's company was the company that put a lot of people in that or employed a lot of people in that town. They were using trichloroethylene, and they had this big unlined ponds, and they would go and dump trichloroethylene there. So all their wastewater was being dumped into these ponds, which would eventually infiltrate and contaminate the groundwater. Okay, so Waltham, Massachusetts, where Grace was working, prompted people to say there is some connection between how we dispose waste and how there could be groundwater contamination. Okay, there is a movie in the 90s, or there is a movie that you can see called Civil Action, and Civil Action is a movie about this very story, and this is the story that actually prompted this case. Actually prompted regulations or people to start saying, what is happening with groundwater. Okay? So before that, before we get to that, there was another act passed, and that act was what's called as the Safe Drinking Water Act, or SDWA. This was passed in like 1974, okay, and got amended several times. 96 was once. What it basically says is all drinking water supplies, okay, if you are going to use a source of water as a drinking water supply, you have to meet certain standards. Okay, so the Safe Drinking Water Act at present regulates about 100 contaminants or so, like 90 plus contaminants. Okay, so it created what are known as MCLs, which stands for maximum levels. Okay, so for all hazardous chemicals, they put an MCL or some limit that says that if you are going to supply water for drinking, you have to have concentrations below that in your water. There is also something called SMCLs. S stands for secondary. And what the secondary MCLs are is, these are mostly based on aesthetic conditions like color, odor, things like that. So they say, okay, you have to keep some compounds within some range to make sure that your water doesn't taste funky or doesn't look different or like it doesn't have a color, things like that. But these are all health based. Okay, and these health based standards EPA is required every 6 years to take a look at that MCLs and then add chemicals to it or remove chemicals to it. To date, there has been one chemical that has been removed from that list. Okay. Several chemicals have been added into that list. Okay. And before they do that, EPA also tells drinking water facilities that you go and regulate some of these emerging contaminants or contaminants that may be carcinogenic, or there is a lab study that says this could be carcinogenic in mice. Let's go and look and see what's happening. So EPA requires them to monitor, and then it looks at that data, and then along with other scientific studies and epidemiological studies, and then comes back and can revise that list. Okay. So EPA can take things out and also put things in. There's to date only one chemical has been removed from that list. Most chemicals have stayed, and more chemicals have been added. There is a big push to add some things like disinfection byproducts. There is a big push to add PPCPs, which are personal and pharmaceutical chemicals. There is a big push to add some flame retardants, so EPA still doesn't have all the data to make an MCL out of it. Partly because some of these chemicals are being detected at very, very, very minute concentrations, nanograms per liter instead of micrograms per liter or milligrams per liter, and as a result, they don't know what the health effects are. Okay. So anytime there is a cancer-causing substance, cancer doesn't happen overnight. It's something that you get repeatedly. You have to have repeated loading over a long period of time. Okay. So that creates a problem in your DNA, which basically means that your cell won't repair correctly, it will repair incorrectly, and then that cell will propagate, and that leads to cancer. So are these nanograms per liter loadings or dosage that humans are getting, is it causing problems, is something that's very hotly debated. Okay? But EPA is looking into some of these compounds and will start probably regulating some of these compounds. The states, so there is something also known as the law of primacy. Okay. So what the law of primacy states is that both for the Federal Water Pollution Control Act or the Clean Water Act, as well as for the Safe Drinking Water Act, EPA, which is a federal agency, which is a central government agency, can basically give the powers to a state agency, okay, and say, okay, we are handing you the responsibility for doing this at the state level, okay, but the state doesn't have the right to change the law, so it cannot change the MCL. Okay, it cannot. If benzene has a 5 parts per billion MCL, and they say, okay, state, now you regulate it. State of California, you can regulate for benzene. We don't have to get involved. They can't change that and say, well, we don't like 5 parts per billion. We're going to take it to 10 parts per billion. They can't do that. What they can do is they'll say, we don't like 5 parts per billion. We're going to take it to 1 part per billion. So they can make the standard stricter than what the federal standard is, but they can never relax that standard and make it lighter than what it was. Okay. So a lot of regulation in the US is done through primacy, which means the EPA actually has the final say. It is the one that is supposed, it is required by law. Congress or the central government will hold EPA accountable for if something goes wrong, but EPA has allowed the states to be managing this because it's a lot easier for a state to manage it locally than it is for the central government to sit there and try to manage it from Washington DC. So because the US is a big country, decentralized management works better than centralized management, but at the same time, to make sure that there are uniform standards, the laws are all set at the federal level. And then the states can adopt these laws or adapt it. They can make it more stringent, but they can never make it less stringent. It's not possible. Okay? So for the first time, when the Safe Drinking Water Act was passed, Safe Drinking Water Act said, doesn't matter what your source is, you have to meet these standards. So it didn't make a distinction between surface water and groundwater. So this was the very first time that groundwater actually got regulated. Okay? And how does it regulate? Basically, if you have a well, okay, and you serve that water from that well to 25 people or 15 connections, Okay, 15 connections means it goes to 15 households or to 25 people, then that automatically comes under the Safe Drinking Water Act. Okay, so you could be a very big municipality that relies on groundwater, has probably about 50 or 60 wells, and you're supplying, like, a city of, a few 100,000 people, like, about 1 million people or so. You have to follow state Safe Drinking Water Act law. At the same time, if you're a very, very, very small town or even a hotel, and you have your well, and there are 25 people living in your hotel, and they're all drinking water from the tap, or there is a potential for them to drink water from the tap, then you have to meet that regulation of Safe Drinking Water Act. Okay, so the range of people that get regulated under the Safe Drinking Water Act is enormous, and one of the big problems is when the standards are very stringent. Okay, so how do we fund treatment systems? How do you think treatment systems get funded? How do treatment systems get funded? Who builds a treatment plant in India? How do they go about doing it? Somebody has to pay for it, right? Like, nothing is free. So when we say, oh, the central government built this, it really we built it, like, because we paid taxes to build it. The same process works in the U.S. So the city or the municipality has to take a loan. Usually it's a very low interest loan, 1% or 0.5% or something, and then they take that money, build this infrastructure, and then charge people. They make money out of water and then pay back that loan. Okay, that's what we call as a debt servicing, or like, so. So typically we build a plant and we say we'll take a loan, and we just can't go, the city can't just go take a loan. In the US, they have to actually have a referendum, they need to have a meeting, they need to ask people, they need to get a buy-in. So either the people vote as a referendum, or the city council that is elected by the people make that decision for them. So so directly or indirectly, the people have to make the decision on whether they want to take a debt and put this stuff. But if the city is providing water, it has to meet the drinking water standards. Okay, so that was the only standard that these groundwater was being regulated to. So the Clean Water Act did nothing for groundwater. This act kind of indirectly regulated groundwater. It didn't come out and say this is a law for groundwater itself. It was a law meant for drinking water. It was saying if you're going to use this aquifer as a drinking water source, you have to follow this law. Okay. The same thing with surface water. So that's what happened. Okay. So there are about 15 million households, or about 60 million people. Compared to India, that's a very, very small number, right? So 60 million people, what is the population in the US? About 350 million people. Okay. So 60 million or 350 million is how much? About 15%. Okay. So about 15% of the households in the US rely on what are called as private wells, which means they have a well on their house and they drink water from that well. Okay. And if they are less than 15 people or less than 25 people or 15 connections, that is not regulated by the Safe Drinking Water Act. So all these people could be consuming highly polluted water, and there is no regulation that's attached with it. And that's what happened in Woburn, Mass. With W.C. Grace, that company was, that town was not on a public drinking water supply. If it was, then it would get regulated by certain things. It was actually a lot of private wells. People were drinking water from a well, virtually untreated, and the incidence of cancer went up. So another act that was passed also in the 70s was what's called as the RCRA, or the Resource Conservation Recovery Act. And this was passed in 76, and subsequently we called it the Solid Waste Disposal Act. It's the same act. And what it says is all solid waste, all the waste that's created has to be managed from cradle to grave. okay, which means you need to know how much waste you're generating, and if you generate X amount of waste, it becomes your responsibility till you dispose of that waste properly. Okay. So for the first time, it put burden on waste generators and said, you are responsible for your waste. Okay. Now, this is only for industrial waste, because as humans, we generate waste. Okay. Are we responsible for our waste? Yes? Really? So if you dispose of waste improperly, will you go to jail? Will you get fined? Okay. Our responsibility is somewhat indirect. Okay. We say we generate waste. Yeah, we generate wastewater, but what do? We usually say there is some other place called the wastewater treatment plant, and we'll just send our responsibility is to send our waste from there to the wastewater treatment plant. As a matter of fact, in US, if you have a house, right, so in a little house, and this is your boundary of the house, and you have a pipe that brings wastewater out of your house, and there is a big trunk or the main line, and it puts your wastewater into that wastewater. Your responsibility is inside your house. So if a pipe breaks in your house, you have to fix it. Okay. If the pipe breaks here, it's city's responsibility. It's not your responsibility. Indirectly, it's your responsibility because you're paying the city taxes, but your responsibility is only related to whatever happens in. So if there is a leak in your house, you better fix it. You can get fined, or you can get, you can get fined. You may even go to jail if it causes somebody else's death, or it can cause some problems for somebody else. But generally, your responsibility ends at your property. Outside the property is somebody else's responsibility. What RCRA says is, now if this was an industry and they generated waste, it's not over. They have the responsibility till it gets disposed of. Okay. So that's what is called a cradle to grave. And they define hazardous waste. How is hazardous waste defined? What are some of the characteristics of hazardous waste? Well, it's ignitable, which means it can catch fire. It's corrosive, or it's reactive. Okay. So one of the things happen then that waste is considered hazardous waste. Okay. So what is one big hazardous waste? What is one chemical that somewhat meets all these criteria and yet is not categorized as hazardous waste? Can you think of one chemical that you probably use, okay, that meets those criteria? You use it on a fairly regular basis. Okay. What's that? Bleaching powder? Possible. It's not ignitable, but it's corrosive and reactive. So petrol, you think it's ignitable? Can it be corrosive? Can it be reactive? It can explode, right? So if you define a hazardous waste, there are very special laws on how that hazardous waste gets handled. Okay. As a matter of fact, you have to take a certification, a 40-hour training, which is like a 1 week worth of training called OSHA training. You have to be OSHA certified to even do basic things with that hazardous waste. Okay. To be even close or work with that hazardous waste. You have to be a certified operator to actually take that hazardous waste and move it somewhere else. But when they wrote this law, they said, hey, there is a problem, everybody in the US has a car, and they all use petrol or gasoline, as we call it there, and they can't be trained, People will throw a fit if I say you have to take all this training because you're using hazardous waste. So what did they do? They said, well, gasoline is not a hazardous waste. We'll just remove it, So they just excluded it from hazardous waste listing. Okay, and the argument was, well, they're not dealing with a lot of stuff. There's not. So a company that deals with a lot of gasoline has to have certified operators who put the gasoline in the tank and stuff. But if you go and pump a little bit of gasoline and a few gallons of gasoline in your car, that's not considered hazardous waste. Okay, so. One of the things about hazardous waste is it has to be properly treated, stored, and disposed in a manner protective of human health and the environment. So this is for the first time. What record did was it said, you cannot. So one of the things that happens is there's something called the TSD, storage, transport, and disposal facility. So you do the disposal, somebody else will transport that waste, and eventually that waste gets stored somewhere in landfill. Okay. The way that law was written initially was it put people who transported the waste, once the waste left your property, you gave away all, so your responsibility was taken by people who transported or eventually stored that waste. Okay. And that was causing problems because said, I don't want to take your risk and transport this waste. So they went and remodified this law a little bit so that the transport people have certain liability, the storage people have some liability, and the people who generated the waste have certain liability. So the liability is now split between all the three operators, because eventually there's somebody creating the waste, somebody is transporting that waste off to a landfill or someplace where it gets stored or disposed of in a proper ways. Okay. So Resource Conservation Act basically said you can't pollute the environment, and groundwater was part of the environment. So this law has implications to groundwater, especially at industrial waste disposal sites where the waste was not disposed of properly before this law. They grandfathered those sites. They said, okay, we can't hold you responsible because the law wasn't there. It's only what you did after the law came into effect that will hold you responsible. Okay. So that again was hotly debated. Some people said that this should become active retroactively, and some people said no, you can't do that, so there were lawsuits and stuff. But essentially what it says is that if you are generating hazardous waste, you cannot be polluting groundwater. Okay. So how do we dispose of hazardous waste? What are some of our choices? Yes, landfills. Okay, so usually we have what are called hazardous waste landfills. These are not municipal landfills where we put our garbage, but there are some specialty landfills called hazardous waste landfills, and they have much higher protection levels of protection. So one of the things that happens is when you put something in a landfill, there's a very good chance that it will leach out and get into groundwater, right? So that created a problem for RCRA operators. They said yeah, I'm a disposal facility, I'll take your waste, you can dispose it off to me, but I can't meet RCRA requirements, because if I meet RCRA requirements, chances are I might be ending up polluting groundwater. So what the state law came out and said is, okay, we understand there is a risk because we are disposing of the waste into a landfill and there is a chance that it will leak. One, we need to make sure that your leachate is not toxic. Okay, you may be storing hazardous substance, but whatever leaches out should not be as hazardous as it is when you got it. So they created what's called as a TCLP, or the Toxicity Characteristic Leachate Protocol test, and then if your waste meets that TCLP, you can go put it in a hazardous waste landfill. Okay, it still can cause contamination. So they said if you do build a landfill, you are required to put a well upstream and put a well downstream, down gradient of that landfill, 2 observation wells at the very minimum, could be more. That will make sure that we know that the minute there was a leak, we are catching it. Okay, so instead of letting that leak go forever, we will protect it as quickly as possible. So the upstream is to kind of say is to make sure that that contamination is not coming from some other source, and the downstream. So if you don't detect something in the upstream and you detect in the downstream, you know that this is the landfill is what's causing the problem. So at that point we can immediately get into see how we can remediate this site and how can we contain the waste. One of the things that happens is that cell of that landfill or that landfill cannot take any more waste. Okay. So there were some very explicit groundwater monitoring requirements that came into play because of the RCRA. Okay. So a RCRA facility or a disposal facility, which is one of those hazardous waste landfills, had to have certain wells, okay, and had to have a monitoring program that says that we will continuously monitor some of these wells. Back in the day when the act came out in 1976, continuous meant once every 3 months. Okay. Nowadays continuous means almost on some chemicals it's almost every day, on some chemicals it's once every 3 months, so on and so forth, like depending on the chemical that you're looking at. But for the first time there was a regulation that said you need to monitor groundwater. Okay, so that was huge. Like this is the first time RCRA basically said you are going to build a facility that can cause groundwater pollution, you need to at least put a monitoring program. So, but what RCRA did not do is it says if there is a groundwater contamination, RCRA doesn't deal with it. Okay. So if I have a hazardous waste landfill, so I have my landfill, something leaches, gets into the water table, creates a little plume, right? We saw this yesterday, right? And there is a well here, a monitoring well. There is also a monitoring well here. This is my upstream or up dip well. This is my down dip well. Okay. I detect contamination here. What RCRA does is you shall shut this operation down. You need to start doing something to make sure that this pollution doesn't go. But this groundwater is contaminated already. Okay. You're required to clean it up. To what level will you clean it up? That is not part of RCRA. What is it part of is the Safe Drinking Water Act. If that water were to be used, if that aquifer were to be used for drinking water, you have to clean it to drinking water standards. If you didn't say, okay, the aquifer is not being used for drinking water, they had to come up with, on a case-by-case basis, what that cleanup should be. Okay, so the states had to come out and say, okay, this is not a drinking water aquifer. What should we clean it up to? Usually, what they clean it up to is they'll go look at what this up dip look like, or that's what the baseline is. It says naturally, if I didn't have this facility here, this chemistry would be very similar to this chemistry. So if I clean it up back to this chemistry, I'm good. Okay. And a lot of times that even that is very challenging. Okay, because once you contaminate a site, taking it back or restoring it back to that position can take several years. Okay. But RCRA by itself was good for groundwater in the sense that it said for the first time you need to monitor this resource if you want to protect that resource. Okay, that's, some people might say, isn't that logical? Like, I need to know, right? Like, if I have to treat the patient, I have to know something about the patient. Like, I have to monitor their temperature, their blood pressure, or whatnot. So for the first time, we said, okay, what RCRA said is if you are going to put a hazardous waste facility, there is a good likelihood that you are going to pollute groundwater, so you better start monitoring. But it did not tell, the regulation stopped short in saying that how much should we clean it up to. Okay. And also RCRA was only good for facilities that came after the law was passed. So whatever pollution happened before RCRA came into play was not part of RCRA. So there were many sites. So when RCRA was passed in 76, it actually came into effect around 1980. Okay. there were many companies that before RCRA came into effect, like hours before RCRA came into effect, took a whole bunch of hazardous waste that they had and illegally dumped, or like, at that point it was legal because the law was not still in effect. Okay, it's only illegal when the law is in effect and you break it. There is no law to break, then everything is legal, right? So they went and disposed of thousands of gallons of hazardous chemicals into ponds, pits, unlined cesspools, wherever they could find. They just got rid of it, because if they hadn't, the law would come into effect the next day and they would be responsible for all that hazardous waste that they had. So what did that do? So one of the good news about RCRA was RCRA protected groundwater starting 1980, but pre-1980 there was a lot of contamination that RCRA created, because if that didn't happen, people wouldn't have disposed of their waste. Like, if they were not held responsible for that waste, they probably would be sitting somewhere in a tank instead of sitting in a cesspool. Okay, so there are a lot of people who are saying RCRA is bad, or like, the implementation of RCRA was bad, because by telling people that I'm going to regulate you starting this day, you gave them an opportunity to get rid of all that stuff illegally beforehand. Like, so a lot of people would have said, like, you should have done RCRA retroactively rather than proactively after the regulation was passed. Okay, if I come in and say, okay, you have a test for an hour, but you cannot cheat in the last half hour of the test, what do you think will happen in the first half hour? Everybody's exchanging questions, right? Oh yeah, what is it? Like, so that's what RCRA did basically. So one other program that comes about RCRA is this underground injection control. So RCRA said, okay, you need to dispose of your waste. Okay, so landfills is one way to dispose it. What are some other ways to dispose of waste? Deep well injection. Okay, so that is the underground injection control program, or the UIC program. Okay, UIC is a little different because it's a separate program, but it interfaces with both the Safe Drinking Water Act as well as RCRA. It interfaces with RCRA because RCRA says there is a way in which you have to dispose your wastewater, hazardous waste, and one way to dispose it is to inject. One way to dispose it is to store in a landfill. And RCRA said, if you are going to do a landfill, you need to do some monitoring. Okay, and the underground deep injection basically says, if you are going to inject your hazardous waste, you cannot inject it into a drinking water aquifer. And it also says that any injection that you do should not harm the aquifer that's used for drinking. Okay. So there is a lot of interest. One other way in which RCRA works is incinerators. Like, so RCRA also regulates incinerators because that's another way to get rid of your hazardous waste. Of course, there are air pollution laws and like NAQA, like National Ambient Air Water, air quality standards that have to be met when you do disposal in that format if you use incineration. But for the purposes of this class, we are more focused on water, so we don't care about air, but that is one possibility.
We can dump in deep sea.
Deep sea? The sea is owned by different countries. Okay. So for a few nautical miles around India, India owns that sea. For a few nautical miles around Bangladesh, Bangladesh owns that sea. For a few nautical miles around this seas. Okay. The deep sea, there are global laws that prevent dumping in deep seas. So people have rights over certain minerals, certain fisheries, certain resources in that deep sea. Although it may not be owned by a country, there are laws and regulations that say the minerals and the resources in this portion of the deep sea belong to this country, it belongs to this country, it belongs to this country. So Dr. Dispose was talking about, Somalia and fisheries, right? Like, Dr. Tortahara was talking about, Dr. Celia was talking about, that's exactly what happened is the Japan and Europe had rights to some of the deep sea near Africa. And the Somalis said, well, you can't come closer to us and take our fish. They said, sure we can. We have laws and permits internationally that allow us to come close to your, we can't get into your country's waters because that's yours, but we can come very close to it. And that's where the Somalia pirates were like saying, no, you can't. So they were trying to use, kidnapping and other ways to stop that fishing from happening, because obviously if they took away that fish eventually would come to Somalia, and Somalis would have the fish, and they didn't have the resources to get a big trawler and go into deep sea and fish for those, catch those fish. So yeah, deep sea disposal is banned. It's a global. There are global laws. People keep very strong track of it because polluting that deep sea would mean polluting fisheries, polluting other things. So countries can't just go willy-nilly and dump something. Okay? Incineration is a possibility. Okay. Again, if the disposal, you still have to store it for a certain while before you incinerate it. The big loss of incineration are mostly air quality loss because you're polluting the atmosphere. But if you do store, you have to store it in a certain ways to make sure that it's protective of groundwater. So RECRA basically, has some guidelines on how these things have to be stored, how should this hazardous waste be stored, there should be double-lined wall containers, they have to meet certain integrity standards and so on and so forth. So underground injection was one thing, and underground injection basically says, here's my aquifer, people are drinking from this aquifer, okay. So I have an industry, and if I want to do deep well injection, I want to inject somewhere much lower strata. Okay. There is something called height of usable water or depth of usable water, and basically it says that what they check to see is where is your injection with respect to the depth of usable water. Okay. And what kind of protections are there? There could be a clay liner here or a shale, something very low permeability, and you basically make your case by saying, okay, I want to inject in a deep well, and before I get the permit, one, I have to make sure that my well is constructed so that it can withstand the pressures that I experience when I go that deep. I'm going several thousand feet deep, like 100,000 to 1,500 to 2,000 feet deep. I need to have a well that can withstand that overburden pressure, but also make sure that whatever I inject here will not cause a risk or will not contaminate this surface water, superficial aquifer. Okay. So if I say I'm going to inject here, I will not get a permit because I'm in the usable aquifer zone. So I have to go much deeper, and I have to make a case. So one thing that is happening that's very interesting is we are all worried about carbon dioxide in the atmosphere, right? Why? It's a greenhouse gas. Anything with green is good, right? Why is the greenhouse gas bad? Okay. So what does carbon dioxide do? Why is it so bad? Traps the sunlight and increases temperatures. Okay. The carbon dioxide is a very interesting molecule because it allows sun to pass, but it doesn't allow the diffuse solar radiation or the solar radiation that happens at larger wavelengths to go back. That causes global warming, right? So we are all contributing to it by breathing out carbon dioxide or portions of carbon dioxide. So do we breathe in oxygen and breathe out carbon dioxide? No, we don't. We breathe in air and we breathe out air, okay? Except that the portion of carbon dioxide is slightly higher in the air that we breathe out. If you truly breathe out carbon dioxide, your nostrils will be gone, you will be bleeding, okay? So because carbon dioxide is very soluble in water, and the minute it touches your skin, it will become carbonic acid and burn your skin, so we still breathe out air, but We've been told a big lie in our high school or grade school or whenever, oh, we breathe in oxygen, we breathe out oxygen. No, we don't, okay? We're not that smart. But anyway, so this is what the deep injection is, and there are standards as to how this well needs to be constructed. There are standards as to where this well needs to go. You need to make a case. There are lawsuits. These people who own this might come out and say this will protect my aquifer. So there is what is known as contested case hearing. So one of the things that's happening, very interesting, is we want to sequester that carbon dioxide. Right? We somehow want to make sure that the carbon dioxide doesn't get into the atmosphere. Okay? One of the biggest sources of carbon dioxide, one of the biggest polluters of carbon dioxide are coal-fired power plants. Okay? So the power plants burn coal. As part of the combustion, they create carbon dioxide and then they put it in. So there is a coal-fired power plant in Houston, and what they did was they said, well, Houston has a lot of people, a lot of carbon dioxide being generated, so we can't really emit this. Okay? And of course, when they burn coal, they're not just emitting carbon dioxide, they're emitting sulfur dioxide, they're emitting other things, all of which are air pollutants. And so they want to take this coal, they want to take this carbon dioxide, essentially make it into a supercritical fluid, which means put it under high temperature and pressure so that it will virtually will become liquid, or looks like a liquid. It's a supercritical fluid, and then flow it down into about 200 miles away from Houston and inject it in the ground in an old oil reservoir. Okay, a place where they were using oil and gas production. Okay. The good news about doing this is there's less carbon dioxide being put in the atmosphere. The good news about doing this was this old deep aquifer, which is down there somewhere, would have some oil still left. So what they wanted to do was they wanted to put another well, and essentially carbon dioxide would dissolve that hydrocarbons, and then they want to pull it out, and this is what is called enhanced oil recovery. So petroleum engineers traditionally do this, where they put in, it's called like carbon dioxide CO2 flooding. They actually inject carbon dioxide because carbon dioxide is very buoyant, and at supercritical conditions it's like a liquid. So, and it doesn't want to be supercritical, so immediately it wants to turn into gaseous state. So it ends up pushing all this oil and getting this oil. So they had to do what is called as a deep well injection permit. Then they had to do what's called as a recovery permit, and they had to prove that this would not cause harm to people living on the surface of aquifer. One of the challenges in that case was this was an old oil field, which means there were thousands of holes or wells that were drilled in over a period of time to extract oil. So the risk was how much of this carbon dioxide will actually get into one of those old wells and contaminate this aquifer. Because what happens if I add carbon dioxide to water? It will form carbonic acid, which will dissociate and form bicarbonate, carbonate, depending on the pH. But if I add acid to water, I reduce its pH. If I reduce its pH, what happens? A lot of things that were not mobile can become mobile. You have changed the reduction conditions. Because if you change your pH, you'll change your EH. If you change your EH, so you will change the valency, and then which is the dominant ion, and so on and so forth. So there was a long, big lawsuit that I was involved with, where we were looking at all this stuff of saying, how can we really deep inject in this well, and if so, what type of monitoring should we do to make sure that these communities are not affected. That is all part of that UIC program, or the laws and regulations associated with that UIC program. What UIC program did not address was what happens to legacy contaminated sites, okay? Which means before RCRA was passed, there was a lot of dumping that went on, illegal dumping. Okay? That was not illegal, it was legal because there was no law. Okay? So that had caused huge amount of groundwater contamination. Okay, a lot of this was happening on very large industrial facilities. It was happening on a lot of military bases, because if you have an Air Force base or a military reserve, there are a lot of chemicals being used as part of that operations. Okay? When people fly planes, you fly planes, and when the plane lands, there is a lot of condensation of water associated with it, because your plane is flying at a very high speed, so through a cloud, and so the cloud condenses onto the plane, like, so you form this ice coating on the plane, and that's just extra weight if you want to take back off. Okay? So they wash that, they have to remove that water from the plane before the plane takes off. And the way they do it is they coat it with some hydrophobic chemical, like, so they just spray either TCE or jet, some other type of organic compound, because it's hydrophobic, and get rid of that water and make sure that the next time the plane flies, it doesn't catch as much water as it does. Like, so when they were spraying all this, all that stuff would just go down, and then go into the contaminants, leach into the ground, create pollution. So there were a lot of sites that what people were doing was perfectly legal, because there was no law saying it wasn't illegal. Okay, but nonetheless causing groundwater pollution. Okay. So we put in Safe Drinking Water Act, and Safe Drinking Water Act basically said, okay, you have a well, you want to use it for drinking water, this is what you need to do. Then we passed RCRA, and RCRA said, you are an industrial facility and you have hazardous waste, and you want to dispose it off in a landfill, this is what you need to do for your groundwater. But none of these laws ever address the question of these legacy sites where groundwater was contaminated because of practices that were once legal. So what do we do at that point? We have to pass another law, so we have to come up with other regulation. So in the 1980, they passed a law called Comprehensive Environmental Response Compensation and Liability Act, or CERCLA. And CERCLA is where risk assessment, environmental risk assessment became popular. So what CERCLA said was, there are so many of these sites that cleaning up every site would essentially bankrupt our country. Okay? There was really no way for us to clean up all these sites. Okay? Which means we somehow have to prioritize and clean those sites that pose the greatest risk. Okay? So we want to prioritize and clean up the most contaminated sites first, and then clean up less contaminated sites later. Okay? So somehow they have to say, okay, what is more contaminated, what's less contaminated? So for that, we created this whole idea of risk assessment. So Ronald Reagan was the president, and he said, well, the way to do it is you look at risk assessment. You have to look and say, what is the benefit of cleaning up that site? What is the cost involved in cleaning up that site? Okay, what is the benefit to cost ratio? Okay, and the benefit was directly related to how much of health risk was being removed because of cleanup. Okay, so the direct benefit was to human health. A secondary benefit was to the environment, so other people who drank that water or were exposed to that water. So we created this whole idea of risk assessment associated with because of CERCLA. Okay. And CERCLA basically says there is some de minimis risk or a minimum risk that we have to accept. Okay. What is that minimum risk? So if I have a cancer causing compound, so it basically said there are two types of compounds. One is carcinogenic compounds, so cancer causing compounds. The other one are hazardous compounds, which are not necessarily carcinogens, which means they can affect your body, they can do things, nasty things to your body, but they will not cause cancer. Okay. the carcinogens are very likely they'll cause cancer. Okay? So they said, even if we didn't have this contamination, people still die of cancer, right? And people can still get cancer. So what should this cleanup do? Because it cannot eliminate cancer. So if we say we want a cancer risk of 0, that's illogical, because people are going to die of cancer anyways. Even without anything, you can develop cancer. And of course, your lifestyle can have an impact. If you smoke cigarettes, your chances of getting cancer increase. If you have a certain type of lifestyle, if you eat certain type of food, your chances increase. So we can control for all of this. So we are going to assume something called as a de minimis risk. That is the minimum risk that we are okay with. Okay? And typically that risk is one in a million, which means if I have a million people, and let's say if I didn't have this chemical exposure, 50 people died of cancer. Okay? What this risk that I'm willing to accept because of this pollution is, the number of people dying of cancer should be 51. Okay? Which means in a million people, only one extra person can get cancer. Okay? So if I had a population that was very prone to cancer, and let's say there were 500 people who were dying of cancer even without the pollution, what this risk says is that can go up to 501 in that million people. So there is only one extra person who should, the risk should be such that only one extra person has a cancer on average. Of course, that varies because it's a random phenomena. But on average, I shouldn't have more than that. That's the de minimis risk. Okay? So if we say this is my de minimis risk, then we back out and say, what concentration can we be exposed to that will keep the risk below that? Okay. So how much of this chemical can we take in, either by drinking water, consuming food, coming into contact when we are taking a shower. Okay. So dermal contact, ingestion, okay, inhalation. Some of these chemicals are volatile, so they may be in the water, but when you heat it up, they'll come out into the air and you will have indoor air exposure. So if you look at across all exposure pathways that you can expose yourself to, the risk should not exceed more than 1 in a million. Okay. So that whole process of risk assessment came out of CERCLA. Okay. Now these are fairly standard calculations. We do it all the time. We assume that people are 70 kilos, they live for so many years, they drink so much water, and they have a certain body mass, and then we come out and say, based on all this, we can say that you can have so much concentration in your water, benzene in your water, or TC in your water, and we don't guarantee that you will not get cancer. What we guarantee is your risk is no more than 1 in a million. Okay? You can still get cancer. Everybody can get cancer. There's a probability, a good finite probability, a very small one, luckily, is that everybody will die of cancer. But our risk that we have increased because of being exposed to this pollutant is 1 in a million. Okay. For non-hazardous, for non-carcinogenic substances, typically we use a 1 in 10,000 risk. Okay. So non-carcinogenic risk could be kidney damage, liver damage, something that causes an ailment to your body, but not necessarily cause cancer. Okay. So the risk assessment all came out of CERCLA. And CERCLA is also called Superfund. It created a fund, okay, and said somebody has to clean up these sites. Okay. What Congress said was, let's try and find who caused the contamination. Okay. But let's not wait till we find out who caused that contamination, because that could have happened 50 years ago, that could have happened 60 years ago, that could have happened 70 years ago. Okay. So it might take us another good 20 years before we find out who actually did it. And even if we find out that person who did it may not have been in business, they might have died, who knows, right? So let's first create a fund, clean up these sites, but let's go after the people who we think caused the contamination. Okay? And if possible, let's recover money from them and say, let's hold them responsible for their act. So, good act, bad act, good way to go about doing things? Yes? Why is it good? It's not good? Somebody said it's good, right? Who's saying it's good? You're saying it's good? Why is it good?
Because there is no other option. Because someone has to pay that.
Correct. But we don't know who that is, okay? In many of these sites, you have absolutely no idea who that is, okay? And secondly, remember, putting it in an unlined, putting a hazardous waste in an unlined pond, as grotesque as it sounds today, was perfectly legal at that point. So, are you going to hold someone responsible for something that was legal when they did it? If I ban water, right? If I ban bottled water in this country tomorrow, okay, and tell, I will go after all those people who drank bottled water yesterday. Is it legal? Is it good? Because it was perfectly legal yesterday to drink bottled water. It was perfectly legal to put that in a lined canal. Everybody knew it was wrong, right? It's like smoking. Go and ask a smoker, they'll say, I know it causes cancer. Okay? Will they stop smoking? I don't know, like, you know, so it's hard, right? Like, you know, so that's how it is. We knew it was wrong, but it was legal. Okay? So many things that are wrong, but as long as they're legal, we get away with it, like, you know. So what CERCLA did was it said, you caused contamination because you did something legal back in the day, but I'm still going to hold you and fine you for it. The only good thing about CERCLA was, so it brought in that retroactive legislation that people were asking RCRA to do. In RCRA, the government said, no, we are not going to retroactively hold people accountable for something. What CERCLA did was it said, we will try, and if we can identify and say, yeah, this person caused this contamination, we will try and recover something. Okay, we will. So there was a shift in the way our regulatory environment was in 76 versus how it was in 80. Okay. But they also recognize that it is a very, very difficult task to find who actually caused the contamination. Okay. So what they said was, let's not wait till we figure out who caused the contamination and they pay for it and then we clean it, because that cleanup may never happen. So the government said, let's find a way to fund and clean up these sites. If we can collect money from somebody else down the road, that's good. If we can find a responsible party, that's great. But if we don't find it, we'll be okay. We'll still okay. One of the things that did was, it said you have a contaminated site, right? So you have a property, and you caused contamination. Okay? Then you sell it to me. Okay? Now, who is responsible for the contamination? You or me? Who should be? The one who contaminated shall be held responsible. Yeah, but you bought it. You are the one who has the property right now. So, in law, the way it usually works is we say, well, you know, I can't go after that guy, but I can go after this guy. So I'll go and see if I can get something from this guy, right? So what CERCLA did was it said, if you buy contaminated property, you will be responsible for it. Okay. You cannot point your finger and say, oh, I didn't do this contamination, somebody else did it before me, like, go after that guy. Was not allowed under that law. Okay. So a big chunk of, a good chunk of environmental business in America is to do what are called these site assessments. So when somebody goes and buys a property, the first thing they will make sure is there is no contamination on that property. Okay. If there is contamination on that property, and let's say you are trying to sell it to me, I have to do due diligence to find out if there is contamination. I have to prove that I have done everything I can to make sure there was no contamination, or I knew of contamination before I bought the property. Now let's say you withheld something from me and said, don't open that door, there is nothing out there, whatnot, and okay, and or you hide something from me, then the responsibility stays with you. Okay. But I have to do my due diligence. I have to say, I have to prove that, no, I'm going to open the door and take a look. Okay. And if I didn't, if I just believed you and said, okay, there is nothing behind that door, I'm going to buy the property, then I'm assuming that responsibility. So I'll become responsible for that cleanup. So one of the things CERCLA said was, if you're a property owner and you're buying something that's contaminated, you better do your due diligence. You may not be able to find that contamination, that's fine, but at least prove to us that you have made every effort to find out whether there was contamination or not. Because if you don't, then you walked into a mess without really doing your due diligence. So it kind of shifted somewhat who the responsible party was. Okay. It also said that, you cannot just blame somebody else for this mess. If you bought it, you have some ownership to it. Okay. So one thing CERCLA did was it gave a lot of business to environmental engineers, but it gave even more business to lawyers. Okay, because now the lawyers will require, that somebody come and do this diligence. They have to write it down saying that we did this due diligence, and then if lo and behold, if some contamination was found, there will be all kinds of lawsuits that are going on, people suing another person, and then trying to figure out what it was. But CERCLA did create that fund. How did they create that fund? They said, okay, what is one thing people are doing in the US? They're all driving cars, which means they're all using petrol or gasoline, so they created a tax on that gasoline. They said, for every gallon of gasoline, I'm going to charge you like 10 cents more, and take that money and put it into Superfund and clean up all those sites that have to be cleaned up. Okay. When the Superfund was made, people called it Superfund, right? Because there was a lot of money in it, and they said, oh, this is Superfund, there's a lot of money. What they realized was that money was not enough to clean up these sites, because one, we had never done any groundwater contamination cleanup to begin with, so we didn't know how to clean it up. Our first guess was, let's pump and treat, because we have ex situ systems. So we have done wastewater treatment plants, they work, we've been doing it since 1975. Federal Water Pollution Control Act showed us how to do this. So we'll pull out, put an ex situ treatment and treat it. Turns out it didn't work out very well. So then we said, oh, we need to do it in situ. We tried doing in situ, and we said, well, that doesn't work quite well either, because we don't know the geology well. Now we do a combination of treatments, we mix and match, we do a lot of different things, but it's been, for the last 20 years or so, or even 30 years now, 35 years, almost 40 years, because 1980 was when this law was passed. We've learned a lot of things on how to do groundwater remediation. But the entire groundwater remediation industry essentially came out of CERCLA. Okay? Because CERCLA basically said, if there was contaminated groundwater, we'll give you money to clean it up, and then figure out who did the contamination. Okay, so these are called legacy sites, or sites where there was previous contamination. And how do we prioritize these sites? Well, we said, we don't have enough money to look at these sites. We created risk assessment, and we also created what's called an NPL, or the National Priority List. And what that National Priority List says is, it says, okay, we're going to look at all these criteria, and if your site meets all these criteria, it gets put on that national priority list. If it gets put on that national priority list, then it becomes eligible for the Superfund. Okay. So there was a broad regulatory framework that was set up to fund national priority list. So you can go on EPA website and Google national priority list, and it will tell you all the sites. It will show you a map. It will tell you which state has how many lists, and it also, if you drill down, it will tell you this site is put on this list for this reasons, for this chemicals. This site is put on this regions for this chemicals, so on and so forth. So you can, all that information is transparent. If you want to get your site listed on national priority list, you have to meet certain threshold scores, and then they will do a public hearing. They'll come and tell people, like, we're going to put this site on national priority list, and so there are debates back and forth, and then based on the criteria they put it. So that's what CERCLA did. And one of the things that CERCLA did not do was, we had gasoline, right? We had petroleum sites. So there were about close to 3 or 4 million underground storage tanks that had petroleum. Okay. And remember, gasoline is not a hazardous waste. Okay. It was excluded from RCRA. Okay. And when that tank leaked, the soil became contaminated with gasoline. Now, gasoline is a mixture of chemicals, so it's got about 200, 250 chemicals. Nobody knows what's in it, but it's got some alkanes, it's got some alkenes, it's got some solvents, so on and so forth. Okay. This is what we call a multi-component mixture, like a very complex mixture. If you ever take and put some gasoline into a gas chromatograph, you will see peak after peak after peak after peak after peak. Coming out till everything comes out, it separates out, and a lot of things don't get separated out very well because they come at the same time, and but so the contaminated soil, gasoline contaminated soil, was not considered hazardous waste because it did not meet that flammability, corrosivity, reactivity criteria. The soil itself was not. You needed a lot of gasoline to burn it, but it didn't. So, but when water moved through that gasoline contaminated soil, it would pick up benzene, it would pick up toluene, okay, it would pick up other things. Once it got into the groundwater, Safe Drinking Water Act said your benzene cannot be greater than 5 parts per billion. Okay. So the groundwater was regulated under Safe Drinking Water Act, but the soil had no regulation. Okay. So it was up to the states, individual states, to figure out what to do with that soil, how to clean up that soil. What the feds or what the Safe Drinking Water law said was, the minute it gets into groundwater, and if it's a drinking water aquifer, by golly, you will be fined. You will be responsible for violating the Safe Drinking Water Act. But we will not touch the source. That's not part of our business. So the states created this UST program, or the Underground Storage Tank program, and it started saying, how can we regulate, how can we clean up these contaminated soils? What was the challenge? The challenge was there were a lot of these sites. Okay, California had like 3,000-4,000 sites, and how many engineers will you think were there in California working for their state environmental protection agency who could deal with this contamination? Remember, there are engineers who have to deal with air, who have to deal with water, other things, probably like 20, 30. Okay? So geologists, engineers, there was a very small team trying to deal with a very large number of sites, and that was complex in itself because each engineer was responsible for like 300-400 sites, which is a lot of sites to clean up at any given point in time. So it created another type of challenge, but there are some state regulations or state laws that deal with contaminated soil, that are offshoots or that have come in because if they don't do that, they'll be in violation of federal laws. So not all laws in the US are federal laws, but some of them are state laws, and the state laws have come up because they have to clean up certain things that are part of the federal law. Okay. So, are they the only sources of contamination? This is all industrial type pollutants. Okay. What about humans? Do we create other forms of pollution? One big area is decentralized wastewater. Okay. So a lot of rural areas, we have what are called septic tanks. So how does septic tanks work? How do they work? What do septic tanks do? Dilution? Anaerobic digestion, okay. What else? So how do you design a septic tank? What do you do? Can we just go put a tank and collect our waste? So one of the things that we do in the septic tank is we have a house, so we somehow still have to collect all that water, our wastewater that we generate, okay, from our toilet, from our kitchen, from our washing machine, whatever, and then we bring it out, take it into a tank, which is called the septic tank. Okay. The way the septic tank works is you put your both primary treatment and secondary treatment all in one place. Okay. Typically, you do primary treatment, which is a physical treatment where you pull out like big solids, and then do the secondary treatment where you're trying to pull out the smaller solids, and then you do some disinfection, right? So here we do the settling, and we take the top portion, which is a supernatant, and have it undergo secondary treatment. Okay. So hopefully it's not anaerobic. Okay. In most American systems, we try to do it aerobic. So what we do is we actually poke holes, okay, right on the top, where the soil is actually getting, so the soil moisture or the air that's in the soil vapor, will facilitate keeping the bacteria alive. If it goes anaerobic, it will start smelling. Okay. So the second thing we do is we can't make this a closed container, because if we did, after 2 days it will be done. We need to build a very big tank. So we somehow have to remove that waste that's being treated. So we put a pipe, slotted pipe, and essentially leach out water once it goes above a certain threshold. So that's called the leach field. Okay. So the idea is you do some treatment here, and hopefully there will be some treatment that's happening in this soil, and any water that goes into the water table is relatively contaminant free. One thing we don't do in a septic tank is we don't disinfect. Okay. But it does both the primary treatment and the secondary treatment. Usually there is no disinfection, no point where we do disinfection. Although in some septic tanks, we can put like a disinfectant unit right here and have it pass through and then do the disinfection. Our goal is that the microbes will take care of it, and there will be enough dilution there. It's because we're not dealing with very large quantities of water. So we have usually carbonaceous material and nitrogenous material that we degrade. Okay. So most of our nitrogen material is in what form? Oxidized or reduced? Reduced. Okay. So we have more ammonium type compounds in our incoming wastewater. Okay. Once we oxidize it, it becomes nitrite and nitrate. Okay. Nitrite is more dangerous than nitrate. Okay. The drinking water standard for nitrate is 45. In US it's 10. Okay. Why? Because it is 10 milligrams per liter of nitrate expressed as nitrogen, whereas is roughly what the rest of the world does. It's milligrams of nitrate. If you write it as milligrams for nitrate, it's roughly 45 or so. If you write it as milligrams of nitrate expressed as nitrogen, then it's about 10. Okay. So we use nitrate nitrogen in the US, rest of the world uses nitrate directly, but essentially they are one and the same standard. Okay. So this is all aerobic, right? So we have ammonia here, or nitrogen is NBOD, mostly ammonium, okay, reduced form or organic nitrogen, right? Comes out, leaches. So we are oxidizing that nitrogen compound, which means we form nitrates. So by the time it gets into groundwater, whether the water gets into groundwater, we have added nitrates. Good or bad? Why? Correct. Okay. So if you have babies and you give them nitrate water with nitrate, the baby will turn blue, like, and it can die. There is some recent evidence that nitrogen, excessive nitrogen, or like long-term exposure to nitrates can cause cancer. They certainly will have some kidney. It also has impacts on kidneys. So there are a few health effects associated with nitrate. Okay. So in most rural areas, we use septic tanks to take care of our wastewater, and we use a drinking water well to take care of our water. Okay. So essentially, again, we are drinking somebody else's wastewater because the upstream septic tank will leach some water into the groundwater and we'll pull it out and we drink it. There are actually laws in Texas. Your drinking water well has to be at least 75 feet away from your septic tank. Okay. And sometimes it's very difficult to do that because you have a house, there's not much space between them. Everybody wants their own septic tank, everybody wants their own well, and there's not enough 75 feet to separate these two. So what do you do in that cases? I don't have money to put a deep well. Yeah, one way to do it is to say, let's avoid the aquifer that the septic tank is leaching into. I'll go deeper and get water from a deeper well, right? But deeper well means expensive well, so I can't do that. Okay. So you have a house, there's not much of a difference, you don't have the 75 feet. So what's the solution? Correct, so somebody can get the septic tank, somebody can get the well. Which one do you want? You want the septic tank? You're the only person in the world who will probably say, I want a septic tank, okay? Nobody wants a septic tank. Everybody wants a well, okay? So they'll say, no, I want the well. So, that causes problems. So decentralized treatment plants sometimes can have major issues, okay, in rural areas, primarily because of that. Most places we don't have this problem in Texas because there's a lot of land, but there are communities where people want to stay next to each other, or rural communities or poor communities that where the houses are very closely spaced, and there's not enough place to put a septic tank and a well, and you have to get into some really creative arguments and bargaining and things you have to do to make sure that people are not in violation of that. But given a choice, nobody will take a septic tank, everybody will take a well. So what other forms of contamination can exist? So it turns out there are 6 general forms of contamination or source types of contamination. Okay? The first category of waste are sources that are designed to discharge substances. Okay, we talked about septic tank. Septic tank is designed to release certain chemicals. Okay, we are building a septic tank so that we are not storing anything. We are treating it and we are disposing it. Okay, so injection wells, the same story. We are designing it so that we can inject some contaminant somewhere. Okay, land application. Okay, people will say, okay, I have wastewater. What do? It's got a lot of nitrogen in it. So instead of buying fertilizer, I'll just put manure on the field, grow crops. But again, I'm intentionally discharging wastewater. Okay, so the city where I live, city of Lubbock, decided that they are a groundwater dependent system. Okay, we have no other water but groundwater. There's no river there. So they were pumping groundwater, lots and lots of groundwater, because the city is about 250,000 people, and they were generating all this wastewater. Okay, so what happens to the wastewater? They can't inject it back into the aquifer, so they have to discharge it. Okay? It's very hot where I live, so a lot of that would just evaporate and be gone. Okay? People said, come on, you're wasting so much water, there is all this water, wastewater, we need to do something, right? So Lubbock created this beautiful park system and said, we're going to take all our treated wastewater and make our parks look green. We have fountains, which we need because that's wastewater, so aeration is a good thing. So if you come into Lubbock, you will see a lot of fountains, and because it's all wastewater being used in our park system. And the city has got a beautiful park system. But still, there was some wastewater. They couldn't use up all their wastewater. So they said, there's still wastewater. What do we do with it? We don't want to put it in. There's no river to put it in. If you put it in some ditch, it's not going to go anywhere. It's going to be a waste. And it's groundwater. We're extracting groundwater, which means we're not recharging that groundwater. So we need to do something with this water. So they said, oh, why don't we use it? Give it to the farmers right next door, and have them do land application. Okay. So Lubbock found a piece of land, got a bunch of farmers, and said, hey, don't pump water because it's expensive. We'll give you wastewater, grow crops. Okay. Of course, you can't grow anything that you want to eat because people don't like eating wastewater, right? In most parts of the world, we irrigate with wastewater. In the US, we don't. We irrigate with somebody else's wastewater if we can. So they said, okay, you can grow cotton because we don't eat cotton, so we'll sell it to some country, China, and they'll make clothes and they'll sell it back to us, and we can happily use it. Okay, and we'll pretend that it never came from our wastewater. So they started giving this water and created what's known as the Lubbock Land Application Site, LLAS. Started growing cotton with wastewater. What do you think happened? Now we have a huge nitrate plume right next, in our aquifer, right where the cotton was grown, because all the nitrogenous matter, which was like an ammonium type compounds, cotton took some of it to grow, but a lot of it was infiltrated, oxidized, went from being ammonia to nitrate, and went into our groundwater. So we have a huge nitrate plume sitting right by our airport where the Lubbock Land Application Site used to be, and that's because of our efforts to reuse our wastewater, which we did not want to waste. So there's a saying in English that says no good deed goes unpunished. So our good deed was we wanted to reuse our wastewater, and we got punished with a nitrate plume. But that happens. Okay, so that's one type of sources. The sources are we intentionally discharge chemicals. There is another type of source, or source 2, where our goal is not to dispose, is not to discharge the substance into the environment, especially groundwater, but our goal is to store chemicals. Okay, we want to store it, but there could be an accidental leak. Okay? So the underground storage tank, landfills, surface impoundments are all categories in that waste. Okay? Our intention is not to discharge, our intention is not to put it out in the environment, but we want to contain it. but in the container can break and release chemicals into the environment. Okay? So that's type of source. Other type of sources that are designed to retain substances during transport. So these are pipes, transmission lines, tanker trucks. Okay? All these are sources where our goal again is not to discharge into the environment, but these things can leak and create contamination. The fourth is sources discharging as a consequence of other activities. Okay? This is urban runoff. Okay? You get a lot of chemicals that get into underground because they're just running off of nearby. Some of it is infiltrating into the ground. Irrigation. Okay? We want to put water to grow crops, but we also put fertilizers to grow crops, and as a result, or if we irrigate with wastewater, we'll end up getting nitrogen contamination. That's one type of source. Another type of sources that provide a conduit for inducing discharge through some flow paths. So I put a well, and I have two aquifers, aquifer A, aquifer B. This is contaminated, but I put a well that goes here. This tracks some contamination here. Now I have contaminated this upper portion of the aquifer. Okay. If I had just not screened it here and just had my well till here, I wouldn't have contaminated it. Or in the other hand, if I hadn't screened it here, I would have just had contaminated water from one aquifer, but not from the other aquifer. But by putting a well that cuts across two zones, I've literally contaminated both the aquifers. As a matter of fact, this is illegal. You cannot put a well like this in state of Texas. Okay? You will not get a permit to put a well that cuts across two formations, especially if you know that this formation is contaminated. So, but that is a possibility that happens. Okay? And the last type of source, the sixth type of source, is naturally occurring sources, which are either created or exacerbated by human activity. Okay? A lot of saltwater intrusion. What's saltwater intrusion? So you have coastal area, you have a land, you have sea, you have an aquifer. Okay? So you have a sea level, right? And you have a land surface. Usually the land surface increases from your sea level. Sea is your lowest level, but you also have an aquifer underneath, and there is a water table. Usually it slopes towards the sea, right? And I'll put a well, start pumping out water. It creates a cone of depression. And it pulls water from all directions. Now it's pulling some of that seawater into my system, which I'm going to. So over time, this seawater actually has, this is my saltwater interface. Okay, that interface will start moving up, because I'm pumping. So this front will start moving inland. Okay. So if I have wells very close to the coast, I'll end up progressively salinizing my aquifer. Okay. Happens a lot in islands. So if you're on an island, you're surrounded by salt water in all directions, right? So you have salt water somewhere here. You have an island, okay? And over time, when there was rain, there's fresh water that infiltrates into this. And is fresh water denser or less denser than salt water? Less denser. So will it float or will it sink into salt water? it will float on salt water, right? So what will happen is it will create an aquifer that's actually fresh water that is sitting on top of a salt water. Okay? Of course, salt water and fresh water are miscible substances, they're not immiscible. So if I put a well and I pump, okay, there is also salt water right here, right? This is my salt water, this is my salt water. So as a pump, the salt water will enter. Okay? And to make up that, some of the salt water from the ocean will enter, and I will progressively salinize it. So there are small islands like Jamaica and other things, Hawaii. When the population was very small, they could sustain themselves on this fresh water because they were not, there was recharge, and their discharge was less than that recharge, and they were okay. But as these islands, everybody says, that's a cool island. I can be on the beach for most part of my life and live happily, right? So they went to islands, and the island populations went up, and the groundwater use went up because there's no other water for them other than to desalinate it, and now they have salt water. Now they have to put desalination plants. There's another thing that can happen, that is, if I have an aquifer inland, not on an island, anywhere basically. So over time, there is geology, there is deposition of various geologic layers. So each year, back in 10 million years ago, my land was here, there was weathering, there is sediments being added on top of the sediments because of wind, because of water. So over time, my elevation has risen, and each time water infiltrates and gets into deeper formation. So this water here is probably a few 100 million years old. This water here is probably 100 million, tens of thousands of years old. This water here is like thousands of years old. This water here is like about fresh water, that's new water. Okay? So this water has been sitting there for a very, very long period of time, like millions of years, hundreds of millions of years. And that water will sit there and react with all the minerals that's out there. Okay? Since it has got a long time for the reaction to take place, what happens is this water gets salty. Okay? So you can have salt water in the bottom and fresh water on the top. Okay? So if I have a system that says, okay, here's my fresh water, right, and here's my salt, this water is salty. Okay, that's fresh water, that's salt water. Okay. So I put a well. Okay, now I want to put a house, and I want to put a well. Where would I put this well? Or where should I put this well? So I want to put a well. So a well, by very nature, is a tube. Okay, plastic. These days, most of the wells are PVC, but you could put it with steel. You could put it with concrete, whatever. We're talking about what's called as a tube well in this country. In the rest part of the world, it's just a well. Okay. We have dug wells here, which are not very popular in where I live in the U.S. But okay, you put a well. That well has a screen. Okay. So this part of the well is called a screen, and this part of the well, which is closed, is called a casing. Okay. The screen is where the water comes into the well. Okay. Either you can have a submersible pump or an overhead pump, and that water gets pumped up. Okay. If I put this screen somewhere in the saltwater zone, obviously I'll pick salt water, right? So I don't want to do that. So before I put the well, I actually drill a hole and I run some geophysical logs, and what that geophysical log tells us is how much is the salt content. Okay. It will tell me where the water is, it will tell me how much salt content is. It gives me an estimate. It's not a true value, but it kind of can tell me this is how much salt is there. And if I see that it's too salty, I don't want to put a well. I'll go back and fill up that hole with cement or bentonite, and then I'm going to put my well here. Okay. So I have salt water here, fresh water here. Would you screen it in the salt water portion? Usually you don't want to, right? Because you'll be getting salt water. Unless you want to run a desalination plant, you really don't want to put it in the salt water. So you put it in the freshwater portion. What happens? I start pumping. What do you think will happen to this freshwater saltwater interface? It'll move up. Okay. So there is some critical level to which it moves up. It's okay. Okay. But if it crosses that critical level, okay, what happens is the water will simply get sucked into this well, because this well has an influence. It's pumping, it's pulling water from all directions, because it's a radial tube. Like, you know, its water is coming from all directions into it, and it's possible that this interface doesn't have to go all the way to the well. It can, if it just rises enough, it will still get sucked into it. If it goes into that zone of influence or the cone of influence, it will get sucked into the well. So till this point, the interface is pretty stable. I can see what the interface looks like. But if it crosses a critical threshold, it becomes unstable and gets sucked into the well, and I start getting salt water. Okay. So this phenomenon is called upconing. So it's not enough that you put a well in the freshwater zone. It's also important that you pump. Okay. You limit your pumping, because if you pump too much, you will end up getting salt water. Okay. Your intention is not to contaminate that water, but this is a source of contamination. It's a source of contamination because it's not your intention, but by pumping, you have increased the water flow. Okay. So that's the sixth source. So we have 6 types of sources. We have many thousand contaminants. Okay. So in the next class, we'll start looking at how can we pump, how can we write equations, or how can we start modeling some of these systems of contaminant sources, and start seeing how should these models be written, what are the processes, things like that. I strongly encourage you to bring your laptops if you have them, because we'll start using models, we'll start writing models. And I strongly encourage you to read through chapter 2 in your notes and try and implement that model that we did yesterday. If it doesn't run, we will look at it tomorrow, but do give it a shot.